in chapter 6, where we are discussing transformation of stresses and strains, failure theories, and thin-walled pressure vessels. This is the second session in chapter 6 and 44th session overall. Here we will discuss transformation of stress using Mohs circle. Here we have a glimpse of the sessions covered in the first 4 chapters. In the earlier chapter, we discussed shear. We are now discussing transformation of stresses and strains. In the last session, we developed algebraic equations for transformation of stress. In this session, we'll discuss a geometric method, the Mohs circle. We earlier mentioned that if an element is rotated by an angle theta in the counterclockwise direction, then the stresses in the rotated element can be found out using algebraic methods or geometric methods. We have discussed the algebraic method. So we have found out expressions for sigma x dash, sigma y dash, and tau x dash y dash. We'll now look at Mohs circle, which gives the geometric procedure. Mohs circle is helpful since it gives the overall representation of the stress for a 180-degree rotation in one view. It can be used to give the direction and magnitude of the principal stresses and the maximum and minimum shear stresses. We earlier obtained this as the expression of sigma x dash. Here we have brought the first term to the left side. Also earlier, tau x dash y dash was given by this expression. We notice that the first part of these two terms on the right are the same, except that there's a minus here. So if we square these two terms and add them, then we'll get this expression. This is because cos squared 2 theta plus sin squared 2 theta is equal to 1. Apart from these two terms on the right, we'll get two other terms which will cancel out because of this minus sign. Here we have squared the left side as well and added them up. In this equation, sigma x dash and tau x dash y dash are unknowns. Sigma x, sigma y, and tau xy are the stresses in the element which hasn't been rotated. So this expression can be written in this form, where x is sigma x dash, y is tau x dash y dash, a is sigma x plus sigma y divided by 2, and this expression is r squared. From analytical geometry, we know that a circle is represented by x squared plus y squared is equal to r squared. So this is the circle with its center at 0, 0. If the center is at A and B, then this is the expression of the circle. So this is the expression of this circle, which has the center as A and B. This is the expression of a circle where B is 0. So with B as 0, the center of the circle lies on the x-axis. So the locus of sigma x dash and tau x dash y dash is in the form of a circle with its center on the x-axis at a distance a from the y-axis, where a, as earlier mentioned, is sigma x plus sigma y divided by 2. This circle is referred to as the Mohr circle. We have an element here and say we like to find out the variation of stress as this element rotates. In order to draw a circle, we need the center and the radius. From the values given here, we can find the center and the radius. So we can draw the Mohr circle. This is the normal stress axis and this is the shear stress axis. However, here we do not know points that this element presents in the Mohr circle. The Mohr circle is drawn in another way. The points related to this element are plotted first. Here, let us consider that the magnitude of sigma x is greater than sigma y. For plotting the Mohr circle, we adopt a convention. The convention is that we plot anti-clockwise shear stress in the lower half of the shear stress axis. Adopting this convention helps us with further analysis. So the normal stress and the shear stress here has been plotted as point A. Tau yx has the same magnitude as tau xy. However, as we can see, it forms a couple in the clockwise direction and therefore is positive. So we have plotted point B as shown. The straight line AB is the diameter of the Mohr circle. It passes through the center of the Mohr circle, which is at a distance of sigma x plus sigma y divided by 2. So now we have the center and the radius of the circle, so we can plot the circle as shown here. The points corresponding to this element are A and B. Consider an element as shown in figure 1, on which the stresses acting are known. We assign the points Q, R, S, T in order to designate the faces. Mathematically, we draw the Mohr circle considering rotation of this element. As earlier discussed, we plot the stresses acting on the elements first. So the stresses acting on the faces ST and QR are plotted as A. Tau xy is anti-clockwise here, which is plotted as negative, as earlier mentioned. The stresses acting on the face RS and QT are plotted as B. AB forms the diameter of the Mohr circle, and now we can draw the whole Mohr circle by rotating the diameter. OA and OB are 180 degrees apart. Perpendicular, these two sides are 90 degrees apart. So rotating the element by 90 degrees corresponds to an 180 degrees rotation in Mohr circle. Or generally we can say a rotation of theta of the element corresponds to a rotation of 2 theta in the Mohr circle. You have to notice that the direction of x of the element and the direction of x in the Mohr circle do not correspond. Now consider that we rotate from the plane OA by the angle to theta 1 in the counterclockwise direction and arrive at the plane OA dash. This corresponds to the perpendicular to ST rotating by an angle theta 1 in the counterclockwise direction. So the stresses corresponding to A dash are the stresses on this face of the element. We extend A dash O to O B dash. Then B dash will give the stresses on this face of the element. Now consider a clockwise rotation of OA by the angle to theta 2 when we reach A double dash. Figure 3, we have rotated the element in figure 1 by theta 2 in the clockwise direction. A double dash gives the stresses on this face of the element. We can extend A double dash O to O B double dash. Then B double dash will give the stresses on this face of the element. So whether we rotate the element counterclockwise or clockwise, we can use the Mohr circle to find the stresses acting on the element. Here we show that we can find out the magnitude of the maximum and minimum principal stress and their direction, as well as the magnitude of the maximum and minimum shear stress and their direction using Mohr circle. This is the same element as from the last slide, and this is the same Mohr circle, which is schematic. From the Mohr circle, we can see that point C represents the highest normal stress. So OC gives the plane corresponding to the maximum principal stress. In this case, we see that if we rotate OA by 2 theta dash in the counterclockwise direction, then we reach OC. So if we rotate this element so that the perpendicular to this face is now at theta dash degrees, then we have reached the plane of maximum principal stress. From the Mohr circle, we can see that at point C, the shear stress is 0. So in this plane, we have the maximum principal stress with 0 shear stress. Also from the Mohr circle, we can see that the point C dash has the minimum normal stress. From OC, we arrive at OC dash by rotating 180 degrees in the counterclockwise direction. So the stress here represents the stress corresponding to C dash, which is the minimum principal stress. Again, there's no shear stress at C dash, and there's no shear stress here. So using the Mohr circle, we can find both the direction and the magnitude of the maximum and minimum principal stress. Let us now look at maximum and minimum shear stress. From the Mohr circle, we can see that the point D has the minimum shear stress. And if we rotate OA by 2 theta double dash, then we reach OD, which corresponds to the minimum shear stress. In figure 3, we have rotated this element so that the perpendicular to this side it gets rotated by theta double dash. The shear stress acting on this face corresponds to the shear stress of the point D. E dash has the same magnitude as D but is opposite in sign. It represents the shear stress at this face, which is clockwise. So using the Mohr circle, we have been able to find the magnitude of the maximum and minimum shear stress as well as their direction. We can see that corresponding to D dash and D, the normal stress is sigma x plus sigma y divided by 2. So here the normal stress on both these faces is sigma x plus sigma y divided by 2. Earlier we considered an element with the stresses acting on it known. We then found out the stresses acting on the element after it has been rotated by theta degrees in the counterclockwise direction. So these were the equations obtained. The equations were obtained by considering the equilibrium of the triangle ABC. We can see here that BC gives the stresses on the face of the rotated element. While we mention rotation of an element, the element is not physically rotated. Now ABDE is an element that has been sectioned out of the structure and is in equilibrium since it's part of the whole structure. This element has also been sectioned out of the structure and is in equilibrium, being a part of the whole structure. Similarly, ABC is a part sectioned out of the whole structure and is in equilibrium. We earlier mentioned that if we rotate this element by 180 degrees, then we'll come back to the same configuration. That is, the same stresses will act on the element. Let us represent the stress on this face and this face as J and K in the Mohr circle. The diameter JK, if it's rotated by 360 degrees, then we'll come back to the same position J and K. It's the same as rotating this element by 180 degrees. Now the center of the Mohr circle is given by sigma x plus sigma y divided by 2. If we consider the principal planes, then the center is given by sigma max plus sigma minimum divided by 2. This is the same with any arbitrary diameter of the Mohr circle. So here sigma x plus sigma y is equal to sigma max plus sigma minimum is equal to sigma x dash plus sigma y dash. So the normal stresses at two ends of a diameter add up to the same value. We earlier discussed about rotating the element from the plane of maximum principal stress. From this Mohr circle, we can see that if we rotate from the plane of maximum principal stress by 90 degrees, we reach the plane of maximum shear stress. In the algebraic equations, we considered anti-clockwise shear stress as positive, while in Mohr circle, we consider anti-clockwise shear stress as negative. So we earlier discussed that if we rotate from the plane of maximum principal stress by 45 degrees in the counterclockwise direction, we reach the plane of minimum shear stress, which is the plane of maximum clockwise shear stress. In this Mohr circle, we can see that if we rotate from that plane by 90 degrees counterclockwise, we reach the plane of minimum principal stress. With the element we earlier discussed that if we rotate from the plane of minimum shear stress by 45 degrees, we reach the plane of minimum principal stress. With the Mohr circle, we see that if we rotate by 90 degrees counterclockwise from the plane of minimum principal stress, we reach the plane of minimum shear stress. With the element we discussed that if we rotate from the plane of minimum principal stress by 45 degrees counterclockwise, then we reach the plane of maximum shear stress, which is the plane of maximum anticlockwise shear stress. We earlier mentioned that we plot the anticlockwise shear stress on the negative half of the Mohr circle. This is for convenience. Analysis becomes easier with this configuration. Demonstrated here. Two Mohr circles are shown. This Mohr circle, the anticlockwise shear stress is plotted in the negative half of the y-axis, and this Mohr circle, the anticlockwise shear stress is plotted in the positive half of the Mohr circle. Now consider this element which is subjected to shear stress only. Such an element is considered to be in pure shear. The Mohr circle for such a case is as shown in these two diagrams. The center of the Mohr circle coincides with the origin. Now let us plot the stress on the face ST. So tau xy here is anticlockwise and is plotted as u here and u in this diagram. There is no normal stress here, and the points u also do not correspond to any normal stress. Let us now consider that this element is rotated by a small angle theta in the counterclockwise direction. The stresses acting on the element are shown. The magnitude of the stresses can be determined using these formulas earlier derived. So we derived a formula for sigma x dash, sigma y dash, and tau x dash y dash. In this element, sigma x and sigma y is 0. So here the first two terms will be 0. As small, sine 2 theta will be small, and sigma x dash will be a small fraction of tau xy. One would remember that these formulas were derived considering anti-clockwise shear stress as positive. So tau xy here is positive. Sigma y dash will be similarly given as a small fraction of tau xy, but would be negative in sign. So here sigma x dash has been shown positive and sigma y dash has been shown negative. From this equation, we can see that tau x dash y dash be a larger fraction of tau xy, since cos 2 theta be a larger value. Let us now plot the stresses on this face in these two Mohr circles. Tau x dash y dash here is still negative and sigma x dash is positive. Tau x dash y dash in this diagram is positive and sigma x is also positive. To move from u to v in this diagram, we move by 2 theta in the counterclockwise direction, while to move from u to v in this diagram, we move by 2 theta in the clockwise direction. We had originally considered the rotation of the element in the counterclockwise direction. So these two movements are in the same direction, while this movement is opposite to the direction of the movement of the element. So this case is more convenient for analysis. Look at different types of problems involving transformation of stresses. Here we are given an element with the stresses acting on it. We are required to find the stresses in the element when the face of the element aligns with this blue line. As we can see from figure 2, the perpendicular to the right face then has to rotate by 20 plus 90, that is 110 degrees as shown. The rotation is anti-clockwise, so theta is positive. We'll first solve the problem algebraically and then using Mohr circle. These are the algebraic equations of sigma x dash and sigma y dash obtained earlier. Sigma x is equal to 0, sigma y is minus 55, tau xy is clockwise on the right face, so tau xy is minus 80. 2 theta becomes 220 degrees, and we find sigma x dash and sigma y dash. Now tau x dash y dash is given by this formula. So again, theta is 110 degrees and we get tau x dash y dash. The sign convention that we are following in the equations and in the Mohr circle are opposite for shear stress. So while this shear stress is negative when we are using the formulas, it is positive when we are using the Mohr circle. Can find out the center of the Mohr circle, which is minus 27.5. The right face, the stresses are 0 and 80. So we have plotted point A. On the top face, the stresses are minus 55 and minus 80. So here we have minus 55 and minus 80. Now AB is rotated by 220 degrees in the anti-clockwise direction, and we reach A dash, B dash. A dash is 2.9 and minus 78.95, and B dash is minus 57.9 and plus 78.95. As we can see, the stresses given by using the formulas and using the Mohr circle coincide. The shear stress calculated here is negative when it comes to the Mohr circle. Here we have an element with the stresses acting on it given, and we are required to find out the stresses that will act on it if it is rotated 30 degrees in the clockwise direction and 15 degrees in the anti-clockwise direction. There's a tensile stress acting in the x direction, a compressive stress acting in the y direction, and a clockwise shear stress acting, which in the case of formulation we consider as negative. Sigma x dash is given by this formula. For 2 theta we substitute minus 60 for the 30-degree case, and for 2 theta we substitute 30 degrees for the 15 degrees anti-clockwise case. So we obtain two values, sigma x dash 1 and sigma x dash 2, the two rotations. Tau x dash y dash is given by this formula. Again, we substitute 2 theta as minus 60 for the 30-degree clockwise rotation and 2 theta as 30 for the 15 degrees anti-clockwise rotation. So we get tau x dash y dash 1 and tau x dash y dash 2. Also in sigma y dash, we substitute 2 theta as minus 60 and 2 theta as 30 and get these values for sigma y dash 1 and sigma y dash 2. These are the stresses we consider when constructing the Mohr circle. Now xy here is positive since clockwise is positive in the Mohr circle. The center is at minus 15 MPa. Point A is 60-50, which we have plotted here. Point B is minus 90 minus 50. So we have plotted minus 90 minus 50. We then rotate AB 60 degrees clockwise and 30 degrees anti-clockwise to get A dash B dash and A double dash B double dash. After 60 degrees clockwise rotation, the point A dash has the coordinates 65.8 and minus 39.9 as shown here. Point B dash has the coordinates minus 95.8 and plus 39.9. These are the same values we obtained earlier using formulation, though the sign of the shear stress is opposite. Rotating 30 degrees in the anti-clockwise direction, we arrive at A double dash with the coordinates 24.95 and 80.8 as given here, and B double dash as minus 54.95 and minus 80.8 as given here. This again agrees with the values obtained using formulation.